On the night of May 31st, 2009, Air France Flight 447 vanished over the Atlantic without warning, taking 228 lives and sparking one of aviation's greatest mysteries. The official cause pointed to weather and an autopilot glitch, but the real story reveals hidden system flaws, sensor failures, and a cockpit overwhelmed by chaos. How did a routine flight become an unthinkable disaster? The answer changes what we thought we knew about modern flight. At cruising altitude over the Atlantic, 3 pitot probes on the Airbus A330 became vulnerable to a hidden threat. These small sensors, mounted on the nose, measure airspeed by capturing airflow. On Flight 447, high-altitude ice crystals entered the probes, blocking the openings and feeding the flight computers with conflicting or impossible airspeed readings. In a matter of seconds, the aircraft's automation reacted. The autopilot, designed to disengage when it can't trust its data, switched off. The autothrust system followed. Now, instead of the computer smoothing out the ride, the jet reverted to what Airbus calls alternate law. This mode strips away some of the built-in protections pilots rely on, including automatic stall prevention. Manual flying becomes necessary, but the aircraft's control logic is less forgiving. The crew suddenly faced an array of alerts: unreliable airspeed, navigation disagreements, and changes in flight control status. The cockpit displays signaled the loss of normal flight law, but did not spell out precisely what had failed. With the autopilot gone and protections reduced, the pilots were left to fly by hand at 38,000 feet, in darkness, over the open ocean, relying on partial information and their own judgment. The chain reaction set in motion by a few ice crystals would test every layer of the system. The Intertropical Convergence Zone, or ITCZ, stretches across the equator like a moving boundary between hemispheres. It's known to pilots as one of the most unpredictable and hazardous areas in global aviation. On the night of May 31st, 2009, AF447 entered this band of turbulent weather over the central Atlantic. Here, warm, moisture-laden air from the north and south collides, fueling immense thunderstorm clusters that can tower over 50,000 feet. These storms generate powerful updrafts, severe turbulence, and sudden temperature shifts, making them especially treacherous for high-altitude flights. Beyond the reach of ground-based radar, crews rely on onboard weather radar to spot storm cells. But even the best systems can miss the smallest, coldest ice crystals carried by the wind far from the main storm. At 38,000 feet, these invisible particles can sweep into critical sensors. Pilots expect rough air and lightning in the ITCZ, but the risk of rapid pitot probe icing was less familiar in 2009. On this night, the combination of convective storms and limited weather data created the perfect conditions for a rare, fast-forming hazard. The external environment set the stage for the technical failures unfolding in the cockpit, turning a routine crossing into a test of every safeguard aboard. Inside the cockpit of AF447, the loss of automation forced 2 first officers into a high-pressure test of teamwork and judgment. Captain Marc Dubois was resting, leaving Pierre-Cédric Bonnin and David Robert to manage a sudden cascade of system warnings. In this moment, cockpit resource management, the backbone of modern airline safety, began to unravel under stress. Both pilots were experienced, but neither had faced a real-world crisis of this complexity at high altitude. Bonnin, at the controls, struggled with the abrupt transition from automated flight to manual handling in darkness, far from land. Robert, as monitoring pilot, tried to interpret a flood of conflicting cues from the aircraft's displays and alarms. The Airbus A330's side-stick design meant each pilot could move their controls independently, with no physical feedback to the other. If both pilots made inputs at once, the system simply averaged their commands, unless one pressed a priority button. During the upset, there were moments when both side sticks were active, sometimes in opposition. The aircraft issued a subtle dual input warning, but in the confusion, this alert did not prompt a coordinated response. Communication faltered. Standard call-outs, "I have control," or "You have control," were missing or unclear. Verbal exchanges reflected uncertainty. Questions went unanswered, and roles blurred as the situation deteriorated. Task sharing, usually a strength in commercial cockpits, broke down under the weight of the unexpected. The absence of the captain in the early minutes removed a key layer of oversight. The crew's divided focus and the side stick's silent independence left the aircraft vulnerable, setting the stage for aerodynamic consequences that would soon become irreversible. At 38,000 feet, the Airbus A330 lost lift and entered an aerodynamic stall, a condition where the wings could no longer generate enough force to keep the aircraft aloft. The angle of attack, the angle between the wing and the oncoming air, rose sharply as the pilot flying continued to pull the side stick back, commanding nose-up pitch. Instead of recovering, the jet climbed briefly, then began to sink. The stall warning sounded repeatedly, but its logic was tied to airspeed readings. As the blocked pitot probes delivered unreliable data, the warning cut in and out, further clouding the crew's understanding of the situation. For more than 3 minutes, the aircraft remained in a deep stall. The descent was not a spiral or a dive, but a steady, nearly level fall. The nose stayed high, the engines at climb power, but the wings could not bite into the thin air. Flight data recorded a continuous angle of attack exceeding 35 degrees, far above the safe range. The vertical speed reached over 10,000 feet per minute. No effective nose-down input was made to break the stall. The jet lost altitude at a constant rate, falling from cruise height to sea level in a controlled but unrecoverable descent. By the time the captain returned to the cockpit, the loss of lift was complete. The aircraft struck the Atlantic almost flat, with little forward motion, confirming the stall had persisted from high altitude to impact. The flight recorders, later recovered from the ocean floor, would provide the data needed to reconstruct this final, irreversible loss of control. Search vessels from France and Brazil began scanning the Atlantic within days, but the main wreckage of Air France Flight 447 remained hidden beneath nearly 4,000 meters of water. The search area spanned more than 10,000 square kilometers, complicated by shifting currents and limited last known position data. Early efforts recovered floating debris, but the flight recorders and most of the fuselage eluded detection. It took a combination of international expertise and new technology to press deeper. In 2011, autonomous underwater vehicles from the Woods Hole Oceanographic Institution mapped the ocean floor in a grid pattern, using side-scan sonar to sweep for metallic traces. After 2 years and several false leads, the main debris field was finally located in April 2011. The data recorders were retrieved from the seabed on May 1st and 2nd, after nearly 2 years in darkness. Their recovery provided investigators with the crucial evidence needed to reconstruct the final minutes of the flight. The official investigation reached its conclusion in July 2012, when France's Bureau d'Enquêtes et d'Analyse released its final report. Investigators traced the loss of AF447 to a sequence that began with pitot probe icing, continued through automation disengagement, and ended in a stall that went unrecognized until impact. The report called for sweeping changes, mandatory replacement of vulnerable pitot probes, enhanced pilot training for high-altitude manual flight and stall recognition, and clearer cockpit alerts for unreliable airspeed. Regulators followed with airworthiness directives, requiring all A330 operators to install more resilient probes and update procedures worldwide. accountability moved from the technical to the legal arena. In April 2023, a Paris court acquitted both Airbus and Air France of involuntary manslaughter, citing the absence of criminal fault despite acknowledged systemic flaws. The families of those lost pressed for further review, leading to a new appeals trial that reopened in September 2025. The proceedings, scheduled to run through late November, continue to examine where responsibility lies in the complex intersection of technology, training, and oversight. On June 1, 2009, Air France Flight 447 disappeared over the Atlantic with 228 people on board. Investigators concluded that ice crystals blocked the aircraft's pitot probes, leading to unreliable airspeed data and autopilot disengagement. The crew, facing conflicting warnings and immense stress, did not recognize the full stall that persisted until impact. It took nearly 2 years to recover the flight recorders from a depth of 3,900 meters, which revealed the critical sequence of events. The BEA's final report in 2012 identified gaps in pilot training, cockpit warning systems, and procedures. While technical fixes and new training standards followed, some questions, such as the exact dynamics of cockpit decision-making, remain unresolved. In 2023, a Paris court acquitted both Airbus and Air France of criminal responsibility, yet legal proceedings continue into 2025. The AF447 tragedy reshaped aviation safety, but its lessons remind us that even with advanced technology, clarity in training and communication is vital for every flight.